Okay.
Okay, let me share my iPad. Okay, last time we already talking about operation amplifier. Quickly try to review a few things you have to know. Okay, so basically that will be displayed the relation between the bandwidth and the gain. So basically, if you're looking at right here, that's what they're talking about, critical frequency. That means for this display, okay, the cutoff frequency is right at this point. And the gain is 100 dB. If you're looking into the frequency, critical frequency, you're going down 10 to a power of 1. That means unit will be in hertz. So basically, in this case, the bandwidth only from 0 to 10 hertz. You cannot do anything with that bandwidth, too narrow. So if you want to increase the bandwidth, that means you can pick any point in here. For example, at this point right here, the gain going down from 100 to 60. That means you reduce the gain. However, if you're going down critical frequency, 10 power of 3, 1 kilohertz, okay? And the bandwidth will be a 0 up to 1 kilohertz. That's only telling you, in order to get the higher bandwidth, then the gain must be reduced at it, okay? And at this point right here, if you're looking into the left, you get a 0 dB. If 0 dB equivalent to number 1, that's what they call a unity gain. And also they can tell you the bandwidth will be 0 up to 10 power of 6 hertz. That means 1 megahertz. That's what they call a unity gain. Gain equal 1. Okay. And on the operational amplifier, in order to get more gain, they have to get the resistor feedback. Okay, that's the resistor feedback. Connect from the output back into the input. Okay, and we already know V2 is negative, V1 is positive. Input connect to the negative, that's what we call inverting amplifier. Okay, V1 connect to ground. V different here, that means the voltage difference between V1 and V2, and they want it to be 0. So V1 connect to ground, 0 volt, and V2 at this point also 0 volt, but that voltage 0 here, they will be get a different name, virtual route. Okay, the different name. This is the virtual route. They not connect to the route directly. However, the 0. Okay, and this is the ground also. However, they need a wire connect direct to the route. That's what they call physical route. Okay, and the current coming in, when they get up into this point here, virtual route, they cannot going down, same potential. They cannot go into the op-amp, high input impedance. So they will be go this way. Okay. And when we're talking about inverting amplifier, we'll be getting to you more detail. Okay. So in here, they already explained to you and they already prove it or something. First thing, you get a 5 volt here connecting to the negative. That's what inverting. And this point we call a virtual route, 0 volt. Okay. And the current coming from input, they go to this point, they go here, and they go up to this point. However, we already know when the current coming in, you get a positive here, and this is a negative. And that negative, that's telling you output here will be negative. Okay, so this current coming down, they cannot go into the load. The thing is negative. So that's why they coming in here. That current I. And also you can get a 0 volt here. And this will be the negative. So you get a IL, that means the load current. When they go up to this point, they coming in here. IL. So they're telling you output of the op-amp will be I plus IL. That's what we call a sink current. What that mean? That means the op-amp pull the current into inside of the op-amp. That would be sink current. If the op-amp coming out, that later on will be short current. Okay? And if you read it, you can see, you can calculate the current I equal V in divide R1. R1 right here. Okay? So you get 5 volt, divide 1K, you get 5 milliamp. Okay? And the closed loop gain, ACL, basically on this circuitry here, ACL minus RF divide R1. That's the closed loop gain. Okay? And if you want to calculate the V out, then you can take the gain times VE. That's what you get, that one here. And if you want to calculate the load current, IL, you take V out, divide to RL. You get 1.5 milliamp. And you're adding up the current I and the current IL, you get the op-amp current. Only thing in here, make sure you understand the inverting amplifier. So input positive, output will be negative. Okay, that's what you get, minus 1.5. Okay, this right here. They will be inverted, opposite. And make sure you know how to get the formula to calculate the closed loop gain equal minus RF divided to R1. Okay, now if you get the voltage Vout, Vout will be the voltage measured from output to the ground. So you get two formula. Vout can be equal IL times RL. And also you can calculate the Vout equal RF times I. That will be negative minus RF times I. Okay, that means Vout measured from output to the ground. That's what you have to understand. So any question about the inverting amplifier? If the input is an AC signal and the output will be AC signal, but they will be inverted, okay, 180 degrees out phase. And last time, we already know how to calculate on this example here. You get an op-amp and they want the gain, you get a minus R3 over R2. You get minus 10. If you get a Vout, you take a 1 volt DC times the gain, you get the Vout. And if you want to calculate the current I, you can take the 1 volt divided to R2, 1K. And if you want to calculate the load current 10K, you can take Vout divide to the 10K. You get the I, you get the I load, you adding up, you get the op-amp current. Okay, and this is just an example for AC. Okay, so Vout, they will be 3.6 volt peak to peak, but you cannot put a negative. The reason is AC, the negative is telling you they will be opposite. If you're looking in the input here positive, output will be negative. Input negative, output positive. So that's why don't put the negative on minus 3.6 volt AC, okay? And now the next one, non-inverting. Why they call it non-inverting? The reason is input will be applied to the positive, okay? That will be non-inverting. Now, if you're looking on this circuitry here, First thing, input have to be right here, not V1 here. Okay, I can say V in right here. Using the voltage divider, then V in will be V1 times 1K divide 1K plus 1K, 2.5 volt. So the input will be 2.5 volt. And you know 2.5 volt, and at this negative here, also you get 2.5 volt. The region is here. VD equals 0. That means VS positive, VS negative, same voltage. But not virtual route anymore. The thing is they not connect to the route. Okay? And 2.5 volt here, you can get 2.5 here. 2.5 and a route, you can easily to calculate the current I here. Okay? In order to get that current, you get I equal 2.5 divide 1K. Okay? Let's see in here. They not show you. I show you. I 2.5. You get 2.5 milliamp. Okay? In here, they given you the gate ACL equal 1 plus RF over R1. So now, let's see. Try to see in here. They prove that, okay, formula. If you get the gain, first thing you know, VL equal ACL times in V in. And also IL equal I plus IL. Again, now, if you get the current I here, basically they're not coming from negative here. They coming from this way. I. And when the current I comes, you get positive here, you get negative here. So in here will be positive, and that will be positive, that will be negative. So basically, this current I will be coming out from op amp. Okay? And positive here, negative here. I load also coming out from op amp. Okay? IL. Okay, this in this situation we call a source. Okay, short current. That means the op amp will be sent out the current. And we can see I out of the op amp equal I plus IL. Okay, that's what they given to you formula here. And A, the gain, closed loop gain, always greater than 1. We know for sure. The thing is they equal 1 plus IF over R1. Okay? And now, let's say more detail here. You can see V out equal IL times RL. And also V out. V out will be measured from here to the route. You get IL, you get RL. You can calculate the V out. However, in order to get a formula, you cannot using the load. That will be telling you V out will be measured from output up to this route here. Okay, so that will be telling you, you take the voltage across RF plus voltage plus R1. Then you also get V out. That's what they're telling you here. V out also equal VRF plus VR1. And the current of V out equal I times RF. That means the voltage here. Okay. Plus V in divide R1. That means the current times R1. Okay. And then you can get V out equal V in times RF divide R1 plus 1. That's what they prove. How come they get this formula for the gain of inverting and non-inverting amplifier? So input positive, output positive. Okay, input negative, output negative. Output and input will be in phase. Okay, so that is the two one we already done. And it's just the non-inverting amplifier, but a different way. They make a connection. This is the V in go to the positive, okay? And also you can get the RF and R2. RF is a feedback resistor, okay? So in this case, current, the voltage gain, 1 plus RF divide R2. Now, also, when you're looking into the op-amp configuration, you must be recognized, is it an inverting or non-inverting? In order to get which one, inverting or non-inverting, depend on the input connect to. If V in connect to positive, they will be non-inverting. If V in connect to the negative, they will be inverted. So for this way, different connection. However, we know that will be RF, that will be R1. So the state set for the circuit shown for closed loop gain. So the closed loop gain, you can see 1 plus RF over RI. One plus 220K. 10K. So what you get? 203, right?
23.
23, sorry. If you want V out, you take the V in times 23. V in equal to 1 peak to peak. They're telling you 2.223 times 2. Okay. If you want the get the voltage go to the 10 kilo ohm. Okay, so they will be equal what? The voltage here, V in equal to volt. And the different voltage here, VD, 0. They're telling you the voltage at this point also 2 volt. Or that will be also 2 volt. So they want the volt current to 10K will be equal to volt by 10K. Okay, so 2 volt divide 10K, what you get?
0.2 milliamps.
0.2, that means 2 milliamp, right?
0.2 milliamps.
0.2 milliamp. This circuitry you will be see all the time. So make sure you understand it. Okay. Okay, any question for the first example? Anything? If you not quite understand. If it not, go to the second one. They want the value of RF. They want this resistor to produce closed loop voltage gain minus 100. Okay, so basically you get the ACL equal minus RF over RI. And they given to you equal minus 100. You already know RI, then that's why you can calculate RF. RI times 100. Okay. That easy one. Unity gain amplifier. This circuitry we call unity gain amplifier. Okay, they have a no resistance feedback. Okay, unity gain amplifier that telling you the gain equal 1. Gain ACL equal 1. That only telling you input, output will be the same. However, make sure you know they get a different name. They can be a buffer amplifier. They can be an isolation amplifier. Or they can be called a follower. Okay. Buffer amplifier, that means input, output will be the same. Okay. Now, isolation amplifier, that will be very important. What isolate? They will be isolate between the input and the output. The region that they get a big impedance. So that's why in most of the power supply, they have to using this unity gain amplifier. For some reason, output is short to the ground. Okay, so the input and the output are isolated. So you don't have any problem. If you remove the ground at the output, and the output will be coming back. without unity gain. If the output short to the ground, they will be cooked the IC right away. Okay, that's what they call isolation. And the next will be summing amplifier. So basically, they're using an inverting amplifier. Try to working with the what they call a summing. What that mean? That means you get a V more input, not only one. You get a V1, V2, V3. Connect to inverted. Okay, that's what output will be, adding them together. So in order to solve the problem, normally you're working with one source at a time. Okay, that means you work first with V1, then later next you're working with V2, and then V3. And that's what they coming up with. This is the formula to calculate the summing. Vout equal minus of the total voltage, no matter what, how many input voltage. However, all of the resistor here have to be the same. That's what they call a summing amplifier. Next, they're talking about slew rate. Okay, what circuitry are we using here? What's the name?
Non-inverting.
Who telling me what is the name for this circuit?
Non-inverting.
No, it's not.
With the follower.
Follower, correct. Unity gain. You get the output connected directly to the negative. No resistance. We just get to it. That means the gain equal 1. There can be buffer, isolation, follower, only telling you what input, output will be the same. Okay? And now, input here, V in, they go from 0 to certain voltage here. However, output supposed to be the same. Okay, only thing, they will be duplicated. How they're not working that way. The output will be going up, okay, but they take a little time, delta T. Maybe 1 microsecond, nanosecond, then they can going up, but they cannot going up exactly like the input. So that's what they're talking about, slew rate. The maximum rate of change of output voltage in response to a step input voltage is the slew rate of an op-amp. The slew rate it depends upon the high frequency response of the amplifier stay within the op-amp. So in order to calculate the slew rate here, they take delta V out, okay, divide to the delta T. And delta V out will be equal plus V maximum minus to minus V maximum. Okay, that means you take a V maximum and plus another V maximum. Okay, the unit of slew rate is the volt per microsecond. So basically, the slew rate is telling you take how long the output will be go to the maximum like the input. Okay, if the small number, much better. Okay, however, if they want to calculate the slew rate, and you know what the delta V out and what is the delta T in here, you can see output of the certain op amp appear. So in the following, in response to a step input, they want to get the slew rate. Okay, now try to explain, see what they explain to you. You understand the delta T that calculate from 10% to 90%. You can see you get a 10 volts here and minus 10. Okay, 10% of minus 10 is minus 9. Okay, so you get the first point here, and 10% of this also 10 or 90%. You can get a second point, and they given to you a 1 microsecond. So output goes from lower to the upper limit in 1 microsecond. The limits are taken at a 90% point as indicated, so the upper limit is plus 9 volt and the lower limit is minus 9 volt. The slew rate equal delta V out divide delta T. So 9 minus 9 divide 1. Micro, you get 18 volt per microsecond. Okay, and now can you tell me, can you do it for me? For related problem. They say when a positive is applied to an op amp, output voltage goes from minus 8 to plus 7 volt in 0.75 microsecond. What is the slew rate? Okay, equal
Is it
delta V out.
20?
Divide delta T. So equal what? Is it
20.
15, right?
20?
I'm talking about calculation. Is it 15 volt divide 0.
Yes.
Point,
70.
correct?
Yes, sir.
Okay, so you divide what you get. Okay, 15 divide 0.75. 20.
Volts
And volt
per
per
micro.
yield second. That's easy. Okay. Gain, bandwidth, product. Let's see what they said in here. An increase in closed loop gain cause a decrease in the bandwidth. That's what we already talked at the beginning. You want to increase the closed loop gain. That will be decrease in the bandwidth. Okay, unity gain bandwidth equal ACL time FC. Okay, now let's see what they try to do here. Determine the bandwidth of each of amplifier. So both of them have an open loop gain 100 dB and unity gain bandwidth 3 megahertz. Let's see solution. So number one, for non-inverted, the closed loop gain ACL equal 1 plus RF over RI. Then you get 67.7. So if you want to calculate the unity gain bandwidth, okay, FC equal bandwidth, okay, closed loop unity gain bandwidth divide ACL 3 megahertz divide to 67.7. That means the gain. And we'll be telling you 44.3 kilohertz. Unity gain bandwidth. That means you want to calculate the FC. Okay. And you get the gain 67.7. Okay. And also they given you unity gain bandwidth is 3 megahertz. Okay. So basically from this formula here, okay, that given to you FC. That's what you want to calculate it. Okay. That will be unity gain. Bandwidth divide to ACL. ACL you calculate, you get 67.7 closed loop gain. Unity gain bandwidth, they gave it to you here, 3 megahertz. So that's what you were able to calculate the FC. For non-inverting, so they will be the same thing, okay? They need to calculate the gain. And also you can take the unity gain bandwidth divide ACL. And that given you the FC equal 63.8. Okay, now let us go with the left volt. We're working on the left volt. And you can see that the different amplifiers show into input circuit. That amplifies the difference between V1 and V2. V1 connect to the inverted. V2 connect non-inverted. When R1, R2, R4, R5, the same value. The different amplify, okay, Vout will be the difference between the Vs positive minus Vs negative. Okay, that means that right now we're talking about differential amplifier, not inverting amplifier, not non-inverting. The thing is they're using both input V1 and V2, so that they have to be a differential. In this case, Vout equals difference between V at the positive minus V at the negative. In practice, the input impedance for V1 equal ohmic value of R1. The input impedance for V2, okay, equal the ohmic value R2 plus R4. You understand this is a voltage divider, okay? Different amplified circuit combine the gain effect from the inverting and non-inverting resistor ratio. Okay, for V1. Okay, now for V1. For the amplifier, you solve for V1, then V2 will be rounded. Okay, if you want to solve for V2, V1 will be rounded. That's what they call superposition. So if you round it here, and now I want to deal with V1 only. So can you tell me, if we're using V1 only, what the configuration of the circuitry? I try to repeat it. This is a differential amplifier. They're using V1 and V2. Okay, to solving the problem, you have to do calculation for V1 only, then for V2 only. If you want to calculate for V1 only, V2 should be rounded. They will be round here. Okay? So now I want to calculate the V1. So what is the configuration for this op-amp?
Inverting.
Remember, right now I'm talking about this will be round. So now if you're looking into that, what is the name of this configuration?
Inverting.
Inverting, correct. You understand inverting. The thing is, the other positive connect to the ground. Okay, what is the gate? What is the gate?
R5 over R1.
Minor.
Minor.
Right?
Yes, sir.
For V1. Gain. ACL. Is it minus R5 over R1? Is it correct?
Yes, sir.
The thing is they will be inverting amplifier. And now if you want to calculate the V out will be equal V1 times the gain. So that's why you can see in here, V out equal minus V1 times R5 over R1. R5 over R1, that means the gain. Okay? If it's confusing or not follow, let me know. You're doing a left vote. You will be go through it. Now, I need to calculate for V2. Okay, when you calculate for V2, V1 will be dropped. Okay, what is the configuration for the op-amp now?
Non-inverting.
Non-inverting. Perfect. Non-inverting. So what is the gain equal? Okay, for V2. ACL equal. Non-inverting will be 1 plus, right? Plus what?
Plus R5 over R1.
Perfect. R1. Okay. And now if you want to calculate the V out, you take the V out. You take the gain times the V in. However, V in not a V2. V in will be right here. I say VA. They have to be connected directly to the positive of the op-amp. So what VA equal? This is just a voltage divider. So VA equal V2 times R4 R2 plus R4. Okay. Then you can take the gain times VA. That's why they calculate for you here. Okay. V out equal V2 times R4 divide R2 plus R4. That's voltage divider. This is VA times the gain 1 plus R5 divide to R1. Okay, that is the calculation for each one, for V1 and for V2. Now, if V1 and V2 equal 6 volt, VL equal what? You telling me?
E.
A or B or C?
B.
C, right? A, B, C, which one?
B. C. C.
I believe the answer will be C. If you want it, you have to calculate the V out 1 for V1. Calculate the V out 2 for V2. Okay? You need to calculate VO1, VO2. Then you can take VO, VO2 minus VO1. Then you can see the answer will be 0. How I can tell you? First thing, they said 12 volts and VA 0. VA cannot be 0, right? VA a voltage divider between 6 volts here. 10K, 10K, you get 3 volts. I know for sure VA equal 3. So that's why that cannot be done. That cannot be. So the answer has to be C. If you're doing a calculation, you get VO in 1 and 2. They will be the same value, but they opposite polarity. So they cancel out. See that? This is the answer. C. Now, see what happened here. In this circuit, sine wave generator apply unwanted common mode input voltage VCM to both circuit input. Due to the common mode rejection of U1, the sine wave does not appear at Vout. This is the noise. Okay, this is the noise that will be affected to V1 and also V2. And you understand how differential amplifier they try to delete common mode rejection. So that's why they say due to common mode rejection, sine wave does not appear at the Vout. Common mode input voltage appear A, across inverting or non-inverting input of a different amplifier, across both input of a different amplifier, A or B.
B.
B, correct. They must be both input, okay, not only one. In this different amplified circuit, R1, R2, R4, R5 are made equal each other due to resistor value. VL equal VS positive minus VS negative, or the difference between the input voltage, okay? The output voltage polarity is determined by the relation between non-inverting input voltage to the inverting. We know that VL equal VS positive minus VS negative. The V2 polarity dominate the V1 polarity and determine the input voltage polarity. Now, on that one, the following relationship apply. U1 is not saturated to the circuit, so VO, V2 minus V1. That means VS positive minus VS negative. Okay, VA equal voltage divider here. Okay, VD, difference between two input is 0. So VA equal VR4. If I want to calculate the VA right here, we already know V2 times R4 divide R2 plus R4. Okay? VA here, that means the voltage measure from positive to the ground, and they will be the same as here. The thing is VD equals 0. That's what I try to explain to you. Now, in this circuit, S1 is used to switch V2 or V1 into the circuit. That means this is a switch in here. Right now, they connect V2. You can connect to V2 or you can connect to V1. Okay, let's see what they say. Vary between 0 and plus 10 volt. Is essentially 0 volt for either at one position. That means you connect here or you connect down here. Okay, they say essentially 0 for either. Vary between 0 volt and minus 10 volt. Okay, both A and C depending on position of S1. On this question of in the left volt, I still confusing. How come they say N plus 10 volt? What they get 10 volt here? I didn't see anything related to the 10 volt or minus 10 volt. Maybe this is a 10 or this is a minus 10. That's what I think. Okay, see what the answer. The answer will be B, essentially 0 volt for either at one position. Okay, that means you get positive here 10 volt, this negative minus 10 volt. Either they connect to V2 or V1. Okay, then the output will be 0 no matter what. Now, the differential amplifier combine input waveform and account for amplitude and the phase. If R1, R2, R4, R5 are equal in value, V1 equal V2 minus V1. You understand that, right? We already know. Differential amplifier, Vout will be different between Vs positive and Vs negative. Based on the circuit information, Vout equal A or B or C or D.
B.
V1 equal V2 equal 2 volt peak to peak. Who get the answer for me?
B again?
A or B or C or D? Just tell me which one, A or B or C or D.
C.
You say B. Who else?
C.
C. You say C. Who else? You get the same answer or not? Basically, if you want it to do it, you have to calculate for V1 only. You get the gain and you time 2 volts. And then you can calculate for V2. However, make sure you have to using a voltage divider. Then you know what is the gain. You get V2 out. The answer will be C, correct? 4 volts. I'm not doing calculation. You have to know how to do that calculation. Okay, so basically that will be done for the operation amplifier. Few things we try to memorize. Inverting amplifier, non-inverting amplifier, follower, summing amplifier. Okay. Okay, if it's not, then we can go to the next one. Okay, so we're talking about active filter. That's a handout for today. Okay. If you already in the last summer and you get a filter, but that will be a passive filter. And now in electronic, you can get same thing, working the same, but they call an active filter. Okay. This one we already know. If you get a period, you can calculate the frequency and the wavelength. Okay. And that will be go with the distance. If you want to learn, that means in the RF, okay, radio frequency. If we try to get on the summer, we get a time, then I will be given a lecture on the RF radio frequency. We'll be talking about how the way your voice transmitted over the air. That's for transmission. And when they reach into your radio, that will be receiver. Okay? It's not hard to do. And this one we already get through it. Only bring it up to you. This is the sine wave. And the sine wave, they get a fundamental. And then they can get a odd harmonic or even harmonic. Okay? However, they just showed you this is a square wave. So the square wave will be made up by more odd harmonic of the sine wave. So inside square wave, you get too many. In square wave, you get too many sine waves. The question is, what is the bandwidth of 1 kilohertz sideways. Basic definition for the bandwidth equal F maximum minus F minimum. Okay, tell me, what is the bandwidth? 1 kilohertz sideways. Who tell me? This is a very, very basic general information you guys need to know. What the bandwidth of 1 kilohertz sideways? Gee, nobody telling me? You don't know? Hello, Mr. Smith. Who know? It's so quiet. Answer to me. You can get a right or you can get a wrong answer. What's the bandwidth of 1 kilohertz sideways? You just still listen to me, right? You hear me?
Loud and
Hello?
clear.
Okay. I want to know what is the bandwidth of 1 kilohertz sideways. Zero. That from Ricky Hunter. Perfect. The answer will be 0. Now, for 1 kilohertz sideways, what is maximum frequency? . 1 1K. What is the minimum frequency? 1K. So that's why you get 0. That will be showing you when you're looking sideways on the oscilloscope. Can you see 2 sideways? No. You see only 1. Okay? On oscilloscope, they can be displayed only 1 sideways at a time, at a different frequency. Same thing. If they're asking bandwidth of 10 kilohertz, they still be 0. And now you can see you get a square wave. Square wave will be displayed on the oscilloscope. This will be displayed on oscilloscope. Okay? So they can be -1 to +1 volt, peak to peak. And this or the other one will be display the same 1 kilohertz square wave. However, they display on the spectrum analyzer. Try to see the difference between the oscilloscope and the spectrum analyzer. Oscilloscope, they time domain. That means they vary with the time. Okay? And the spectrum analyzer, they vary with the frequency. You see that? Happy frequency. And now you can see this is a 1 kilohertz. Okay, square wave. And basically inside, they get more sine wave. And they make up by odd. Okay. Let's see. They will be odd harmonic. So if you get a 1 kilohertz and the third harmonic will be 3 kilohertz. Okay, and the odd, that means 5 harmonic, they will be 5 kilohertz, and so on. Okay, so if you want to calculate the bandwidth of 1 kilohertz square wave, then normally you have to understand what harmonic you want up to. Okay, that means they're telling you, okay, I want a bandwidth for the square wave up to 5th harmonic. Okay, that will be telling you, okay, you take the frequency up to 5th harmonic minus the frequency at 1, and you get the bandwidth. Okay, so basically you want to calculate the bandwidth for the square wave. You will be using the spectrum analyzer. Okay, this is a different display. Okay, let's see. You can see the basic fundamental 1K. This is the third harmonic. They will be 3 kilohertz. Okay, and this will be 11 harmonic, 11 kilohertz. So when they want to calculate the bandwidth, then you have to ask them which harmonic you want up to. If they say 11 harmonic, then you take 11 minus 1. Okay, then you get 10 kilohertz. The display you see that will be on spectrum analyzer. Now we're talking about filter. Filter, they get two different. Passive filter, active filter. Passive filter in AC circuitry. They're using capacitor, inductor, resistor. That means they don't need any power. That's what they call passive filter. However, filter can be working using op-amp. And an op-amp, you already learned it. They need positive, negative power supply. That's what they call active. Okay. Filter are circuits that are capable of passing signal with a certain selected frequency while rejecting signal with other frequencies. This property called selectivity. So basically, when you tuning your radio to different channel, that means you select the filter, okay, to select a certain frequency. Active filter is transistor or op-amp combined with passive RCL circuit. The active device provides voltage and the gain, and the passive circuit provides frequency selectivity. That means when you select, you change the frequency. That means you change the value of the passive component, RCL. Okay. The four basic category active filter. You get a low pass filter, high pass filter, band pass filter, and band stop or notch filter. So basically, you get band pass, low pass, high pass, band stop. Only 4. Okay. First thing they're talking about low pass filter. This is a low pass filter. This stands for the gain. 0 dB equal to what number?
One.
What equivalent? Number 1. The thing is when you take 20 log of 1, you get 0. Number 1, that means at this point in here, V out equal VE. Gain equal to what? Okay. And this is the bandwidth from 0 up to what frequency we call a cut-off frequency. That is the bandwidth. That means they allow the signal to get through the filter. Okay? The other get a different frequency, they try to reject it. That's the ideal. Of the filter. But we're not working with the ideal. We're working with practical filter. Okay. This is mid-range gain. Okay. Mid-range gain 0 dB. Okay. Gain equal 1. That means input coming in 10 volt, output coming 10 volt. The gain is 1. And that's telling you no loss. Okay? When they set 0 dB, that means no loss. In, coming out. 10 volt coming in, 10 volt coming out. Okay, however, at a certain point here, they call it add cut-off frequency. FC means cut-off frequency. The output will be down 3 dB, minus 3 dB, minus 3 dB, equivalent to 20 log of 0.707. That is minus 3 dB. When you do any calculation, you cannot using minus 3 dB. They equivalent to 0.707. Or we can say 70.7%. Okay. So if you get an input is 10 volt, at the cutoff, what the V out? If you get a 10 volt here, what voltage at the minus 3 dB?
7.07.
7.07. In order to get 7.07, you take 10 times 0.707. So at the cutoff frequency, they're going down. Okay? Only 707. You get lost some voltage. But after the cutoff, after that, they want to say stop band. They don't want anymore. Okay? They only allow the signal able to transmit it from 0 up to FC only. Okay? After the cutoff, they don't want any more. However, in here they given you the same thing, slope. Try to understand what that means. Slope equal minus 20 dB per decade. That means they will be going down at a slope 20 dB per decade. Decade means 10. Okay? So that FC, okay, when they going down 20 dB per decade, FC, if I say 1 kilohertz, example, 1K. So 10 times of cutoff will be 10 times FC. In this case, 10K. Okay. And they're going down 20 dB per decade. So if I say I want the voltage, okay, at 20 dB, how do I get it? I say I want the voltage. At 20 dB. You already know how to calculate the voltage at the cutoff frequency. And now it's the 10 time of the cutoff, mean if you get a 1K cutoff, you get a 10K, 10 kilohertz. I want voltage at 10 kilohertz. How do we calculate it? You know the voltage will be 10 volt. At the cutoff, voltage going down to 7.07 volt. And now the question is, at 10 times of the cutoff, that means at 10 kilohertz, what we out? How do we calculate it? Okay. You have to find out how come you get minus 20 dB. Log of what number in order to get minus 20 dB? What number in here? So if 20 log of 1, what you get? If number 1.
Zero.
Okay. 20 log of number 1. 20 log 0.707. 20 log 0.1. Can you calculate that for me? I know log of 1 will be 0. 20 log of 0.707, you already get
Negative
minus 3 dB, right? If you take 20 log of 0.707, you get minus 3 dB. What happens if you take 20 log of 0.1?
Negative 20 dB.
Exactly, minus 20 dB. So they're telling you when you're going down minus 20 dB, that the number will be 0.1. So you want to calculate the output voltage. You take 10 volt times 0.1. That's what you get, 1 volt. That will be telling you at 10 times of cutoff frequency in this case, the output voltage will be 1 volt. The reason I know 1 volt, the thing I have to using the 20 log of 0.1 that coming up with minus 20 dB. Then I take 0.1 times the maximum voltage, in this case 10 volt. So that's why you get 1 volt. You have to understand later on, you have to calculate the minus 40 dB or minus 60 dB. Okay, any question up to this point? Okay, if any question? If it's not, okay, try to read next before we get a meeting next week. We try to finish that also. Okay, so I stop share. Okay, so you get any question to me, anything? Make sure tomorrow, Tuesday, Wednesday, Thursday, you get the lab. Okay, either take 1 or take 2. Take 2, you have to try to get the lab. The lab done as much as you can. If you get a problem, let me know. And we can see the guy in the class to help you. Okay, if you just text to me and try to see which day I can be in the lab. Okay, if no question, then good night, everyone. Okay,
Thank
good
you,
night.
sir.
Good night.
Good night, Mr. Pham.
Good night. Thank you.